Computing Nash equilibria in the tree graphical games. In this section, we described the first and perhaps most basic algorithm exploiting the advantages of graphical game representation for the purposes of equilibrium computation. The case considered is that in which the underlying graph G is a tree. While obviously a strong restriction on the topology, we shall see that this case already presents non-trivial computational challenges, which in turn force the development of algorithmic tools that can be generalized beyond trees to obtain a more general heuristic known as Nash prop. We first described the algorithm tree Nash at a high level, leaving certain important implementation details unspecified, because it is conceptually advantageous to do so. We then described the two instantiations of the missing details, yielding one algorithm that runs in polynomial time and provably computes approximations of all equilibria, and another algorithm that runs in exponential time and provably computes all exact equilibria. We begin with some notation and concepts needed for the description of tree Nash. In order to distinguish parents from children in the tree, it will be convenient to treat players' vertices symbolically, such as u, v, and w, rather than by integer indices. So we use MV to denote the local game matrix for the player identified with the player vertex V. We use capital letters to denote the vertex players to distinguish them from their chosen actions, for which we shall use lowercase. If G is a tree, we choose an arbitrary vertex as the root, which we visualize as being at the bottom, with the leaves at the top. Any vertex on the path from a vertex V to the root will be called downstream from V, and any vertex on the path from V to any leaf will be called the upstream from V. Thus, each vertex other than the root has exactly one downstream neighbor or children and perhaps many upstream neighbors or parents. We use UPG of V to denote the set of vertices in G that are upstream from V, including V by definition. Suppose that V is the child of U in G. We let G to the U denote the subgraph induced by the vertices in UPG of U. That is the subtree of G rooted at U. If V in the closed sets between 0 and 1 is a mixed strategy for player vertex V, and V equals to V to the U will denote the subset of payoff matrices in M corresponding to the vertices in UPG of U, with the modification that the game matrix MU is collapsed by one index by fixing V equals to V. We can think of an NE for the graphical game G to the U and V equals to V to the U as a conditional equilibrium upstream from U inclusive. That is an equilibrium for G to the U given that V plays V. Here we are simply exploiting the fact that since G is a tree, fixing a mixed strategy V for the play of V isolated G to the U from the rest of G. Now suppose that vertex V has k parents, U1, U2, U3 until UK, and the single child W. We now describe the data structures sent from each UI to V, and in turn from V to W. On the downstream path of a tree Nash, each parent UI will send to V a binary valued table T of VUI. The table is indexed by the continuum of possible values for the mixed strategy V in the closed interval between 0 and 1 of V, and UI also in the closed interval between 0 and 1 of UI, where I equals to 1 to 300k. The semantics of this table will be as follows. For any pair VUI, T of VUI will be 1 if and only if there exists an NE for G to the UI and V to the V, capital V, equals to small v to the UI, in which capital UI equals to small ui, little ui. Note that we will slightly abuse notation by letting T of VUI refer to both the entire table set from UI to V, capital UI to capital V, and the particular value associated with the pair VUI, but the meaning will be clear from the context. Since V and UI are continuous variables, it is not obvious that the table T of VUI can be represented compactively, or even finitely, for arbitrary vertices in a tree. For now, we will simply assume a finite representation, and shortly discuss how this assumption can be met in two different ways. The initialization of the downstream path of the algorithm begins at the leaves of the tree, where the computation of the tables is straightforward. If U is a leaf and V its only child, then T of VU equals to 1 if and only if capital U equals to little u is the best response to capital V equals to little v. Step 2, C of figure 7.1. An algorithm tree Nash for computing NE of tree graphical games. Assuming for induction that each UI sends the table T of VUI to V, we now described how V can compute the table TWV to pass to its child W. Step 2, D2 of figure 7.1. For each pair WV, T of WV is set to 1 if and only if there exists a vector of mixed strategies, U arrow equals to U1, U2, U3 until UK called a witness. For the parents, capital U equals to U1, U2, U3 until UK of V. For the parents, U arrow of V, such that the two conditions hold. 1. T of VUI equals to 1 for all 1 less than equals to I less than equals to K. And 2. Capital V equals to little v is the best response to capital U arrow equals to little u arrow, and capital W equals to little w. Note that there may be more than one witness for T of WV equals to 1. In addition to computing the value T of WV on the downstream path of the algorithm, we will also keep a list of the witnesses U arrow for each pair WV for which T of WV equals to 1. Step 2D2 of figure 7.1. These witness lists will be used on the upstream path. To see that the semantics of the tables are preserved by the computation just described, suppose that this computation yields T of WV equals to 1 for some pair WV, and let U arrow be a witness for T of WV equals to 1. The fact that T of VUI equals to 1 for all I, condition 7.3 above, ensures by induction that if capital V plays little v, there are upstream Nash equilibria in which each capital UI equals to little ui. Furthermore, V is the best response to the local setting capital UI equals to little UI capital U2, capital U1 equals to little U1, capital U2 equals to little U2, and so on until capital UK equals to little UK. Capital W equals to little W prime. Condition 7.3 above. Therefore, we are in equilibrium upstream from V. On the other hand, if T of W V equals to 0, it is easy to see there can be no equilibrium in which capital W equals to little w, capital V equals to little v. Note that the existence of an NE guarantees that T of WV equals to 1 for at least one WV pair. The downstream path of the algorithm terminates at the root Z, which receives tables T of ZYI for each parent, capital YI. Z simplified computes a one-dimensional table T of Z such that T of Z equals to 1 if and only if for some witness Y arrow T of ZYI equals to 1 for OI, and Z is a best response to one arrow. The upstream path begins by Z choosing any Z for which T of Z equals to 1, capital Z choosing any little z for which T of little z equals to 1, choosing any witness Y1, Y2, Y3 until Yk to T of little z equals to 1, and then passing both Z and Y1 to each parent Yi, capital Yi. Passing both Z and Yi to each parent capital Yi. The interpretation is that Z will play Z, capital Z will play little z, and is instructing capital Yi to play little yi. Inductively, if a vertex V receives a value little v to play from its downstream neighbor W, and the value little w that capital W will play, then it must be that T of WV equals to 1. So capital V chooses a witness U arrow to T of WV equals to 1, and passes each parent UI, capital UI, their value little ui, as well as little v. Step 3 of figure 7.1. Note that the semantics of T of WV equals to 1 ensure that capital V equals to little v is the best response to capital U equals to capital U arrow equals to little u arrow, and capital W equals to little w. We have left the choices of each witness in the upstream path are specified or non-deterministic to emphasize that the tables and witness lists computed represent all the NE. The upstream path can be specialized to find a number of specific NE of interest, including player optimum, NE maximizing expected reward to a chosen player, social optimal, NE maximizing total expected reward summed over all players, and the welfare optimal, NE maximizing expected reward to the player whose expected reward is smallest. Modulo the important details regarding the representation of the tables T of WV, which we discuss next. The arguments provided above establish the following formal result. Theorem 7.3. Let Gm be any graphical game in which G is a tree. Algorithm tree Nash computes a Nash equilibrium for Gm. Furthermore, the tables and witness lists computed by the algorithm represent all Nash equilibria of Gm.